Page of notes, you get a little bit of a sense of deja vu here because it looks real similar to this page of notes that we had about a week or so ago. Except that that page was position time graphs at the top of it. This is velocity time graphs. You know that if we have a velocity time graph, velocity has to go on the y-axis because the y-axis heading goes first in our title and the x-axis goes second. You also know that time would be the manipulated variable and velocity would be the responding variable because it's always responding versus manipulated variable. The shapes of these graphs are exactly the same as the shapes that I drew for the position time graphs. We want to first identify, not remember, but identify by thinking about each of these graphs, what each of them mean, and then we want to figure out how to determine some of the properties of these graphs, the velocity, the average velocity, the acceleration, whatever the case may be. Now, I want you to remember this. I'll take you back to those position time graphs. A straight line, regardless of the type of graph, position time graph, velocity time graph, momentum time graph, whatever, a straight line means what? One word. Yep, constant. It means constant something, right? Now, a straight line on a position time graph meant constant velocity. A straight line on a velocity time graph doesn't mean constant velocity. If you look at this graph, this velocity is changing, right? The velocity is just a little bit right here, but it's a lot more right here. So this velocity is changing. It's not a constant velocity. What's constant then? The acceleration is constant. We're going to say that this is a constant, or we could say it's a uniform acceleration. Now, by rights, we probably should say that it's a positive acceleration here, right? A uniform positive acceleration. It means it's speeding up. It's accelerating, it's speeding up. But at a constant rate. You can have a non-uniform acceleration. You can speed up at a non-constant rate, but this is speeding up at a constant rate. We're not, be careful here. The speed is increasing, but the rate at which the speed increases isn't increasing. Does that make sense? You're speeding up by the same amount the whole time. Now, what's this next one? That's a straight line as well. That should be uniform acceleration, right? Well, it is technically uniform acceleration, but what value would that acceleration be? A uniform acceleration of 0, which means it's stopped. Doesn't mean it's stopped. No. If this was a position time graph, it's stopped. This isn't stopped. Look, the velocity is something. So what is it then? Yeah, we're going to say this is constant velocity. We're going to say it's constant velocity there. Now that third line, also a straight line, means constant or uniform something. Acceleration, right? What's the difference between the first one and the third one? What is it, Blake? Yeah, this is a constant negative acceleration or uniform negative acceleration. I'm going to write it up here because kind of running out of space at the bottom. Uniform negative acceleration. Now, this next one's a little bit tricky. You could say here that the velocity is increasing, it's accelerating. Yes, that's true, but we want something a little more specific. Is it a constant acceleration? No? So what is it then? Were you nodding your head no? Or were you just kind of stretching your neck there? No, I was saying no. No? Okay. So what is it then if it's not a constant acceleration? Yes, it's a changing acceleration, right? Is it increasing or decreasing? It's getting steeper, so this is going to be an increasing acceleration. Think about what that means. Let me give you a wording that is kind of confusing, but then I'll give you an example that might make a little bit more sense. The rate at which the velocity changes, that's acceleration, right? The rate at which the velocity increases. Do you understand what I just said? The rate at which the velocity increases. So the velocity is increasing, but the rate at which it's increasing is also increasing. If you put your foot on the gas pedal of your car, okay, let's assume that you, because there's a transmission in the car and there's gears and like this isn't quite true, but Let's simplify it a little bit. You got a little go-kart. You put your foot on the gas pedal of the go-kart. You accelerate, right? If you put your foot on the gas pedal and leave it in the same spot, you keep accelerating. You keep speeding up, right? But if you put your foot on the gas pedal and you keep putting your foot further and further down, just a little bit further and further down, not only does your speed increase, but the rate at which your speed increases. Does that make sense? That's an increasing acceleration. Versus this last one, which would be what? This would be a decreasing acceleration. This would be a decreasing acceleration here. Are we slowing down? No, not at all. Look, the velocity is getting bigger throughout this graph. It's just that it's not getting bigger as quickly. So the rate at which the velocity increases, fill in the blank. The rate at which the velocity increases decreases. So the velocity is increasing, it's just not increasing as quickly as it was near the beginning of the graph. If we go back to our example for a second with the car, you put your foot on the, like you floor it. You take off at a really, really quick acceleration, and then you kind of ease off a little bit with your foot. Okay, you're still speeding up, right? But you're not speeding up as quickly as you were when your foot was on the floor. Make sense? So that's a decreasing acceleration. Still speeding up, still accelerating, but not accelerating at as quick of a rate as you were before. Now, there's a few things that we can find from these graphs, from any of these velocity time graphs. One of them, I haven't even mentioned it down here, one of them is velocity. If I want to find the instantaneous velocity, the velocity at one moment in time, what do you think I'm going to do? Give you a hint, it's 3 words. Up and over. If I want to find position on the position time graph, it's up and over. Velocity on a velocity time graph, it's up and over. I don't even have a spot to write that, so if you want to write it down, go ahead. I'm not going to write it. What do you think you're going to do to find the acceleration? Remember, to find the velocity on a position time graph, it was delta d over delta t, which amounted to the slope, right? The acceleration on a velocity time graph will be, you know this, the slope, yes, the slope, or, what is it? Yes, delta v over delta t. We can say the slope, or A is equal to delta v over delta t. It's exactly the same thing, right? Delta v is the same as delta y, delta t is delta x, so delta y over delta x is the slope, rise over run. Now I'm going to skip displacement for a second and go straight to average velocity. The average velocity, you know this too. How do you find the average velocity anytime, in any context, graph or otherwise? The average velocity is always displacement over time. Well, that begs the question, how do we get displacement? This is the hardest one. This is the hardest thing we do on any graph in Physics 20. The displacement on a velocity time graph is the area between the line and the x-axis. So in other words, this area right here. Okay, that area corresponds to the displacement. You can find area, right? You did area in what, grade 6 or something, grade 5? The area of a rectangle is length times width, or base times height. The area of a triangle is 1/2 base times height, or sometimes you say base times height divided by 2. You can do that. Now, unfortunately, sometimes there's more than one shape that you have to find the area of, so it's quite a bit of work sometimes, but still, each one of those calculations is not so bad. All right, let's take a look at an example. This is example number 12 in the booklet that you got on first day. It says, use the following information to answer the next 3 parts of this question. 3 parts? Man, I should have made this question longer than that. You're asked for the acceleration of the object in the third stage, the displacement, and the average velocity. I should have asked you for 4 parts. I should have asked you for the velocity at, let's say, let's pick one here. The velocity at, let's make it at 10 seconds. What is the velocity at 10 seconds here? 20 meters per second. What if I said, what's the change in velocity between 15 and 20 seconds? Change in velocity between 15 and 22 seconds. We would say 0 minus 20 is neg 20, right? Would be the change in velocity. Okay, you weren't asked for that, but you could be, and that wouldn't be that hard, right? Velocity is up and over. Change in velocity would be up and over, and then subtract the two. We're asked for the acceleration, though. The acceleration during the third stage. The acceleration here, I'm just going to do it on this page so I can see everything here. The acceleration here, I'm going to say delta V over delta T. Although you could, if you prefer, use rise over run because it's the same thing. Delta V during the third stage here goes from 20 down to 0. So I'm going to say it's final minus initial, or 0 minus 20. Now my time interval here, we're going from 15 seconds to 22 seconds. So my time interval would be 7 seconds. Does that make sense? Negative 20 divided by 7 is 2 6/7, which I believe is 2.83, 2.85. Negative, though, it's going to be, right? Meters per second squared. And the negative just means, in this case, that it is slowing down, right? Slowing down. It doesn't mean it's going backwards, right? The velocity in all of these, the velocity is positive. It's a positive velocity. You're moving forward, but you're slowing down as you move forward. What did B ask me for? The displacement from start to finish, probably the toughest part of this. The displacement from start to finish. How do you find the displacement on a position time graph? On a position time graph, displacement is up and over, subtract. Displacement on a velocity time graph is the area. In the area, this is a bit trickier, especially this one, because we've got like this crazy shape here that's going up, straight, and then down. Let's break it into 3 sections. Let's call this number 1. Let's call this number 2. And let's call this number 3. Area 1 is a triangle. So we're going to make it 1/2 base times height. The base goes from 0 to 7. The height is 20. So that gives me an area or a displacement in the first stage of 70 meters. In the second stage, it's a rectangle, so we'll say base times height. We're going from 7 to 15, so my base is 8, and my height is 20. That's going to give me 160. And the third one, that's a triangle again. So it's 1/2 of the base, which is from 15 to 22. And the height goes from 0 to 20. 20 times 7 is about 140. Times 1/2 is 70. So what's my answer for question B? What's the displacement from start to finish? 70 plus 160 plus 70, right? It's 300 meters. So my answer for this is, for the total displacement, is 300 meters. Now, if you happen to have a line below the x-axis, it would actually be a negative displacement, right? If it went like this. This was your graph, and it went like this. This would be a positive displacement, and this would be negative down here. So you'd add a positive to a negative. We don't see that very often in physics 20. We do in physics 30, but not so much in physics 20. Finally, question C asked us for the average velocity. How do you do that? Same as you did for position time graph, right? Same as you did for all your homework questions that you found average velocity on. Exactly the same. How do you find average velocity? Displacement over time. The displacement is 300 meters. The time from start to finish here, I think we were looking for the displacement over the whole thing. Oh, that is nasty. See what I did there? The average velocity over the first two stages. Oh, that was dirty right there. The displacement is not 300 meters over the first two stages. What's the displacement over the first two stages? Yeah, 230, right? 70 plus 160. Divided by the time interval is 15 seconds. So we're going to say 230 divided by 15. What does that work out to be? I don't have my answer sheet in front of me. What is it? 15.3. Thank you. Oh, that is definitely, if you look at the back wall there, there's this red boxed off 6 letters, RTQ, ATQ. I don't know if I asked you what those mean yet. Did I ask you what those mean? No? What do they mean? What does RTQ, ATQ mean? Read the question. What does ATQ mean? Answer the question. Read the question. Answer the question. I almost didn't read the question there. The question says, what's the average velocity during the first two stages? I got to pay attention to that, right? And I got to answer the question that's being asked, not just what I think is being asked. Oops. Does that make sense? All right, your homework for tonight. I'm going to give you, this is going to sound like a lot, but it's really not that bad. Worksheet number 5. Questions 1 to 8. Really, that's 2 graphs. Okay, 2 graphs that I want you to analyze. There are more questions than that. You don't have to work any further than that, okay? Just questions 1 to 8.